of a mathematics, where we can say showing the same type of a behavior. So we are actually clustering them. So we create this as a clustering analytics. Then there is a classification analytics. So in classification, we mostly have a labeled data, and where we are actually somehow forcing our algorithm to make the it's a special case of clustering, actually, the classification algorithm, because in classification we are actually we are actually making the weights of different algorithms in such a way so that it actually pushes, or it actually forces the whole scenario to group under those labels, what labels have been given in a classification. So in a training model, then anomaly detection. Anomaly detection, you can say it's probably those data rows, or those when I say data row, that means one observation, because in case of data sciences, every time one observation, we every time write one observation in a one row. So when I say one row or one observation, these are interchange terms we can use. So anomaly detection is the behavior which is quite different, probabilistically quite different, where probability of finding this type of a behavior from any other cluster, any other classification, or any other data inside my database is different. So that's a type of anomaly detection. Then dimension reduction. So dimensional reduction is one which also comes under the big data, how we reduce dimensions and all that stuff. And then feature selection. So now going inside, I mean, everyone. So for example, because here more it will be more on the technical terms, I mean, how we are solving the problems and what are the different algorithms and all that stuff in each. So therefore, let's start with the descriptive analytics, or where we are saying it's a diagnostic analysis, where actually we are we had a data set. I mean, let us suppose that we have given some data set, and where actually our main focus and particular focus is to find why something is happening in this data. So let's suppose, I mean, yesterday I was giving example of that when we have been given a turbine data, and they are saying that, hey, when turbine runs for some time or for a longer hours, it is getting heat up. Or I was giving the example, let's suppose that we have girls and boys, and we saw that the girls are outperforming boys every time, and then we look for the different variables and come up why actually it's happening. So this type of analysis, where we mainly look why something happened, I mean, what are the reasons behind it, it's called as a descriptive, because we go into its description and find out, I mean, try to find out the reasons why something is happening. For example, so how we can actually look into it. So first thing is we can go into a visualization, so we can directly visualize. For example, here I have shown one is a histogram. This is example histogram, for example, for some data set, and so here we can actually say, okay, this is coming from a normal distribution, so my distribution is normal, it's a bell curve. So so the most of things are in the expected range, what we expect, I mean, they will be, but sometimes you will get a negatively skew data, and sometimes you will get a positive skew data. For example, if you see when you are joining the for example, new job, and I'll actually somehow try to plot your skill, what skill you are actually gaining in that new job. So if I go for that and try to draw that, initially the skill where at the rate you are learning some skill will be very high. It will be very high, and after some time you will reach some saturation level where there will be nothing new for you in that job. So for then after that you will not learn that much, but you will get an experience, you will have other but in a skill set you will not have that much of things to gain now, because you are almost already expertise in. So such type of a data, if you draw on a plot, you will get a positive skew, because initially, or it will have more skewness towards right. So similarly, you can have a negative skew. Now there is one more thing where actually we can analyze. So univariant description of, in this thing we take each variable independent of each other. For example, let's suppose I had to find the age mean age of my class. So I don't actually take any other thing whether they are from a, when I question someone, can you give me what is the mean age of your class? So they will not actually go tell me that girls have a mean age of this, and I mean, then they will not categorize, and those students which are performing good, their mean age is this, but they will not go into that. They descriptive analytics on a univariate. They will not see between the collinearities and all other things between different variables, but they will directly go and target the variable which is our target variable, for example age here in my example. And mean, mode, median, percentiles, range, quartiles, interquartile distance, and variance, standard deviation. All those are very much important. Those univariant descriptors, they are very much important. So, for example, my personal favorite is a percentile. I mean, sometimes you will be actually surprised or amazed, hey, how only one percentile we can make one problem statement to show our customer with only one of these univariant descriptors. For example, let us suppose, I mean, I will give a real time example. For example, the customer came to you, and he's saying that, hey, I'm actually the seller of turbine machines. Actually, I will give an example of turbine machines. Can you actually give me some marketing term where I will actually force my customers who have taken turbine from me to actually do servicing from us, so that they can come more for a servicing, or at least they will come to know that their turbines are not performing at well, without showing data to them of other turbines. So I mean, there are different ways to do it, but the simplest way is I will tell them, okay, give me the performance data of all your customers who have taken turbines from you, and give me their runtime data. For example, right now, I'll take a runtime and I'll see. I will just go into a percentile and find where percentile performance of each is. For example, if someone is running for a 500 hours, and while the other guy who had taken the same type of a turbine performing under the same conditions and is running 600 hours per day, so definitely each turbine is behaving better than the one who has a 500 working hours. So rather than showing him 500, 400, I will show the percentile, in which percentile, right, your turbine is actually. So if we find that, hey, his turbine is in a below 20 percentile, so he will say, why there is something happening actually with my turbine. That's why my turbine is not performing better. It's not going into a upper 100 an upper 10 percentile from, for example, from 90 to 100. So definitely he will come back and to the customer for servicing. He will say, hey, can you look on my turbine, why it's not performing better, though it is working under the same conditions what all other turbines are working. So this is how we actually do sometimes marketing with only these univariant descriptors, where we are not going into the deep. We are just taking univariant descriptors and we are saying, for example, mean sales for this year, where for example, and sometimes mean is not that much very well for us, so we go mode. I mean, which, for example, you have to actually target customers of a age group. Their mean doesn't make any sense, but mode will be the more useful statistical term for us, because we will target only that customer in which we have a maximum mode. For example, mode is actually the number of frequencies in case of statistics. So I mean, obviously, from last few days, most of the people are giving lecture on these things. So, and besides, these are some statistical, basic statistical. So hope most of the people know among you about these terms. And if few people doesn't know, so they can go and read it from a statistical. So they are very good. I mean, good terms to define your data set, preliminary analysis. Now there comes one more thing. So then we also sometimes measure of association in discriminant. For example, simple thing is that, like, the size of a home increases, that means its cost increases. So this is a correlation. So we don't have to do that much hi-fi in it, and simply, I mean, we go for a correlation, or we go for a collinearity. How when the two or more than two variables are showing the same behavior. So for example, we know that experience increases, so mostly our job salary also increases. So they are directly correlate. So sometimes we can actually say that this two or more than two variables are negatively correlated. For example, if we see with the aging, our this strength decreases, our muscular strength as well as our will to anything decreases with when we go in an older age. So we can say as age decreases after some limit. I mean, let's suppose after our young, when we be after, I mean, let's suppose 25 above, our strength and our age is showing negative correlation to each other. So then regression. So sometimes we are actually checking between the regression. This is again the simple. For example, their size of this house, as well as the rooms in number of a house, or the location changes, accordingly the price will change. So these are some then risk ratio and a priori analysis. I mean, a priori analysis is I can say it's one of the analysis which is very least used these days, and actually if people use, it's a simple one, and it increases a lot of a value for our data set if we use a priori analysis. I don't know how many people among you know that there is a one famous a priori analysis which probably Salesforce.com or any like this firm did on when they find out that if someone is buying beer, and they always go for that other, there was some other, actually I don't remember the name of other accessory they used to always buy with that. So whenever they go for the first item, they always buy that second item. So this is called a priori analysis, where we actually see how many times one regular item is coming and showing the direct association with the another item. For example, it helps in our marketing. You will see that so when you go in a supermarket, you will say, for example, onions are placed I mean intelligent supermarkets, not in every supermarket. So you'll say onions are placed always on the side of a potatoes. So because how they know, because the owner of supermarket have actually analyzed things over the time. He knows that when someone is buying onion, he always buys potatoes, because both of these crops are those which remain for a huge time at home also, and they don't get wasted like this. So because their we can say their lifespan is more than other vegetables, so mostly people take them together, and that's why they place them close to each other, so that you can have a in view both of these items at the same time. So this is one marketing strategy. So I can say this a priori analysis, this helps us creating in an item set. When we create an item set, and then it also makes a association between the two. How many times this item set we are getting, how many times we are getting X, Y, Z together, how many times we are getting X, Y. So the probability of getting this to the probability of getting the whole item set. This all
Sorry. Sorry for the interruption.
Yeah.
Are you sharing the slides? We couldn't. I couldn't get any slides here.
Oh, so I'm sharing. So okay, let me share. Does this problem is happening with everyone else? I mean, anyone seeing my slides or no?
Yeah, it's visible, sir.
I'm able to very clearly.
It's visible, sir.
Okay, I say okay then. Right.
Yes, it is visual.
Okay.
Yes, it is visible, sir. No problem. Carry on.
Oh, so this.
Sorry.
Yeah, no worries. No. So a priori analysis, I mean, this is one. It's completely actually separately one complete branch under the data analysis, and I actually encourage you people to go and use a priori analysis on most of them. And believe me, it is helping us even to, to find out what are the variables which are very much important for us. So it's very good. Sometimes even our use cases ask for a priori analysis. For example, we have to actually let's suppose that we are working in an industry, and where people are coming and they are raising different requests. For example, they are raising different requests. They are saying that our systems are not performing good, and let's suppose Microsoft Word is not performing good. and now another guy come and he's raising request, hey, okay, Microsoft Word is not working for me, also Microsoft Excels are not working for me. And then again another guy come, and let's suppose they raised some requests, and then when we go in a priori analysis, I can actually say when a people are raising request for that their Microsoft Word is not working, at the same time their Microsoft Excel is not working. So then for both of these two cases, there is a one case which is actually rising them both together. So from that thing we can actually say, hey, actually the root cause for both of these issues is the same. So that's why they are every time coming in same, they are raising request for the same. And sometimes you will see, okay, let's suppose that they are their mobile phones are not I mean, for example, let's suppose they raise requests about mobile phone, they say that speaker is not working, and at the same time they say that our this network is not working. So then they can say that actually the root cause is same for speaker and network. It's hypothetical situation, I'm just giving a hypothetical, let's suppose that. And in these ways, this a priori analysis is very good to actually go and find what all are the issues which have the same root cause, or which at least have some probability of having the same root cause. So important things to take care when we do actually the descriptive analysis. So data must be representative. So when I say data must be representative, it because when we take a whole data set, that's called as a population, for example, and then we work on a small samples, that's called a sample data set. This sample always should represent my whole data set. For example, a simple example is like that. You want to do analysis on a students in a university, and you went for a university for collecting data, and you have to ultimately come with some analytic report on that. You talk to the people in a class, and ultimately you talk to the 100 students in a class, and you give some inference, or you ultimately reached some inference, and you said, hey, okay, this is my inference on students. But at that time, the students you spoke to is not actually the population of university. I can say it's the population of a class, but not population of a university, because in university there is a cafeteria also. In university there is a playground. In university there are different curriculum activities going. In university there is a lab also. So if you actually have to say that it is a sample of a university, then you have to go and talk to the cafeteria people also, and cafeteria students sitting in cafeteria. You have to go and talk to the people who are not never attending classes also, who are always sitting in hostels. So you have to talk to them also. You have to talk to the people in ground. You have to talk to the people in these classrooms. Then I can say, okay, my data is actually the representative of data. Otherwise it's not. Otherwise it's a biased sampling. So another thing is we have to actually deal with the outliers. And let's suppose that I have to go for I'll go in some village, and I have to find out what is the average salary of that village. Let's suppose most of the people are earning between 1500 to 4000 rupees, and there is one officer actually who out of a blue earning 50,000 rupees. And then you come up with the average, and I say what is the average salary, and their average salary will come, let's suppose, near about 7,000 rupees. Though I know that most of people are earning in the range of 1,500 to 4,000, and their average should be somewhere between this range. But because only the one person or two persons are very good officers and they are earning very high, so whole scenario got upwards, and this is the effect of outlier. I mean, this you can easily imagine. Now if government have to formulate some policy on the basis of that average salary, ultimately this will be a very wrong policy, because they never took care of the outlier at the first place, and this outlier has completely vanished our importance of our this survey. So there are open and or undefined scores. Sometimes you will see some observations, they never actually complete those observations. They are half-handed observations. They actually they are not completed, and if we add those uncompleted, they always add a bias. So we have to actually dealt with them, and we have to use a proper level of arrangement, so measurements. So as I say, for example, sometimes mean will make more sense for me, but most of the times maybe mean doesn't make sense, median will make. Sometimes median even doesn't make, mode may make. So it all depends on your problem statement. If I, in simpler terms, for example, I say average age, you have to formulate, I mean, for some school you have to formulate some policy, and you have to actually target different age groups. So at that time, for me, rather than mean, it will be better to formulate them in modes. So for example, different ages have different modes. For example, 10 to 6, 15 to 19, 19 to 20, and 20 to 25. So at that time, it makes me more sense to have a modes rather than mean. So now predictive analytics. I mean, you from last few days you may have heard about predictive analytics multiple times. So predictive analytics predictive analytics. If we say it's working, I mean, simple. It's working is like we get a data, and in a previous data what we have collected or past data, we are actually doing some initial analytics to find out what are the things and how they are happening, and then we, from those things, we are actually predicting what is going to happen in future. So actually there we need some algorithms to do. For example, the famous use cases are famous where we are using predictive analysis for now is illness and recovery. For example, a patient goes to a doctor and he has some type of behavior he is showing. Let's suppose he has some physical illnesses, and then doctor can actually see those analysis, and he is actually in mind how doctor is saying that, hey, you have to actually take these medicines, otherwise in future you will have this problem. Because in mind he is actually processing the past data set, what he has learned from a past experiences. He is actually making that to count there, and that's how he's predicting, okay, in future if you don't treat it like this way, in future you will have this problem. So this is how he is predicting. So it's pretty much useful right now. We can actually predict from x-rays. I mean, you have seen a lot of work is going in MRI and medical imaging, where the people where we can initially predict from X-rays, CT scans, or USG reports. We can predict, okay, this person is suffering from this, and if doesn't treat, he will have this type of a problem in future. So this all is it has a huge booming field in medical field, this predictive analysis. So another is mostly banks are using it. They are predicting whether the person can actually pay back the loan or not. So this is one more predictive analysis. So how they do, they actually go and find out how that person have behaved in past. What is his past history? When he took the loan, does he pay it? Is he paid on time? What were the sources from he was getting the income? So that's why right now they are actually, some banks are going and visiting your locality and finding out how much is your property. Then only they will go, because they use all those predictors to find out whether you are going to pay ultimately or not. So recommendation products. So definitely, I mean, on my visit history to different websites online, they can actually predict whether what I'm going to buy next actually. So that's why you will see that lot of whenever you visit Amazon or you visit Flipkart site. So let's suppose 5 or 6 times you visit, and 7th time you visit, and they will pop up for you. Okay, this is also right now people are buying this thing also. People are, so actually they are somehow forcing us to buy that, because they know our history, our search history, what we have searched. And alternative events, I mean, most people have not used it in this alternative events, but predictive analytics can be used for example, to find alternative events. So alternative events, for example, to find out whether because we have already seen, let's suppose the people having 2 or 3 jobs in a queue, and finding different salaries, what different salaries are being given and what different compensations are being given by different companies, we can actually predict alternatively whether this employee is going to join our team or not. This is called as alternative events. So commonly used algorithms is regression. I mean, regression, most of the people will be very much aware of the regression. So because it's simple one, it's the algorithm where you can actually correlate it in your mind also. I mean, you can think of these because it has a, it's not that much tough where everything is going behind the black box, but inside this regression you can actually imagine the things, because human mind always accepts the thing which they imagine. So if we imagine in a regression, we are actually good to go with the regression because we can imagine it in our, we can create those linear equations in my mind also. And so that's why you will see that most of the people are using this regression in very widely. And after regression there is decision trees. So decision trees, people are also using decision trees these days. So it's pretty much useful, I mean, decision trees. But in decision trees, some things you can't create in completely in our mind, because decision trees maybe have a depth of so many nodes. So it depends how many nodes. So sometimes you can't even visualize everything in your mind. And then there are some classifying algorithms we are also using for predictive analysis. For example, sometimes we use Bayesian theorem, or Bayes theorem you can say, or Bayesian classifier you can say. So you will be, I mean, amazed where, for example, let us suppose that you had to actually find out whether the customer will churn out or stay with us. Some we have some, let's suppose we have some industry, we are selling some products, and for that product we have seen, let's suppose I'm giving that example of the people who are giving us these different internet services, and they actually want to predict us on whether we are going to, I say, regression trees, regression decision trees, and classifying algorithms and neural networks. These are some of the algorithms we are using in predictive analysis. So now if we jump to actually the, so now trend analytics. So this is the something which I mean most of the people are using these days, because it's a time series data, and sometimes it's a very it's a real time data. Most of times it's a real time data. For example, in the main focus in it to look for the consistency in a change. For example, we had a sales, I mean, let's suppose that I'm the owner of one shop, and I had a sales of a clothing last year. For example, if I had data of everyday sales, and I want to predict what will be this my sale next day. So at that time, mostly I'll go with, because it's a time series data, I have actually collected it with the time tags. So I'm definitely going to use some time series models to find out what is going to be the sale next day. So this type of data, where we take data against the time series, and it forms some type of a curve, some type of a line along the time axis. This type of a data is called as a trend data, and we do analysis on it called as a trend analysis. So in trend analysis, one thing is very much notable, is that the most of the terms there are either auto-correlated or partial auto-correlated. When I say auto-correlated and partial auto-correlated, that means every other term which comes is always dependent on the previous term. So for example, earnings, if I take my earnings with respect to the time, so every time my earnings will be actually dependent on what I earn in the previous time. So because in that way, this analysis makes, I mean, it's tougher than other analytics, because you don't have to play with so many variables. You have to play with the variable already. So that is why it mostly, I mean, most of the times you will have heard term forecasting. For example, weather forecasting, market sales forecasting, not a market sales prediction, but forecasting, because we are forecasting this on the basis of its own variables. So So mostly in this we have a time series data. Let's suppose that now what are actually the types of a time series data? What functions can be fitted on them? Sometimes linear graph, sometimes it will have an exponential growth, sometimes it may have a logarithmic growth, sometimes it may show a sinusoidal growth, and sometimes sigmoid. I mean, most of you people will be very much aware with those functions in mathematics, what we are used for them. Now the key points I will tell here is, first is the decomposition. So decomposition of a time series. Let us suppose that we have a time series data of sales. We have a time series data of sales. So when we are doing sales, most of the people know that the sales of clothing is very high in the earlier months of summer, and sales of clothing is again high in the earlier months of winter, when winter starts, because people mostly go. So if we see, this is called as a seasonality. So for example, even if we see in a temperature, if we see in a temperature is high in I mean most of the parts of India between maybe from May to August. So it's pretty high, and then from August it starts decreasing, and then again from January it starts slightly increasing. So this type of analysis, doing this type of analysis on my data set is actually called seasonality. So in order to do analysis, we always do decompose our time series data into different layers. For example, first to remove seasonality. So because we know that seasonality is repeating again and again with each interval of time, and interval of time will be different. For example, it may be months, it may be years, and sometimes it may be only minutes. So for example, performance of a these turbines, or performance of these flow engines. So in flow engines, it may be only of a few hours, where it is again reaching to the same point. So this type of behavior is called as a seasonality. So whenever we do to any we have to do any analysis, we have to always remove seasonality, and sometimes we have to also remove the cyclic natures which are repeating, because most of the analysis, as I say, they depend on their previous values. So we want stationary time series data to do all those analysis. So then noise removal. So there will be always some noise removal, and you apply some masks on that. So mask applying is like we have a actually we can say that a shifting window will have a mask on it, so it will keep moving there. Just give me 1 second actually. So yeah, sorry, there was actually my friend was asking for some things, that's why. Okay, so decomposition, we remove those cyclic effects, or we remove those seasonal effects. Then we have a noise. So for noise, mostly we do masking. I mean, in order to learn it, people have to go actually into it and learn how we do masking on a noise. And then there will be some random things which you can't even explain how they are coming in our time series. So few things here. So one of the famous model here using for time series analysis is RIMA, auto-regressive integrative moving average model. So auto-regressive is taking care of auto-correlation actually. So because we are doing regression on its own terms, and moving average similarly taking care of these partial autocorrelations, while we are actually taking them as independent, and then finding out the averages. And the term integration is actually the differential, which type of a differential you will use initially, for example. So first differential, second differential. So first differential, what does first differential in time series mean? Let's suppose that we have a data from t to tn. So what we do minus tn minus 1 to tn. So we make one interval up and then do minus it from the whole time series. So this is called as a first differential. And if we move to we do first differential and then again to this first differential, we again move first time interval and slide their time series towards left and take the minus from the original time series. This is called as a second differential. I mean, after differentials, most of the time my time series will come as a stationary time series because it will take care of these seasonalities and all that stuff inside it. So I think, I mean, I know that these will be these terms will be some naive terms initially, but once you will start working in a trend analytics, these are very good things to work. I mean, these are very good and even to learn. I mean, you will find them very interesting. So then after trend analysis, the one more analysis we are actually going for clustering. So this is the something which most of the people are doing. I mean, other than classification, this is the clustering is nearly everyone who is coming in data science only after a few days they start doing this clustering. Clustering is actually the segmenting of data. And what segmenting? Segmenting of data on the basis of some features which are actually same or sometimes showing same behavior between different observations. So this type of actually, if I say working, so working is like you are finding initially you are actually converting your observation into the dimensions. What dimension here means? So here each dimension means each feature, and each feature for us means each variable. So we already know that. Let's suppose that our data is of a 10 dimension. That means it has a 10 features. So any data, for example, if I want to check the performance of a student, it's not only the marks getting in a class, but let's suppose that it's a marks getting in a class, it's a behavior by a student showing in a class, it's a activity taken by a student in a curriculum activities, and it's the overall exposure of a student. Let's suppose these are the 4 features on which we are actually segmenting the students. So these 4 things comes, these 4 features are actually dimensions for me. Then what I will do, I'll actually measure the distance between the between different dimensions. So I'll measure the distance, and every time I try to have a small intercluster difference, and I mean, I somehow behave in such a way that I will cluster them in such a way so that the intercluster distance will be small and the distance between different clusters will be high. That's how we are also finding the cluster centers. So that's one other discussion. I mean, how, but this is the, I mean, on the overview terms, you can see like that we are always trying to reduce the intercluster difference, and we are trying to actually increase the intra-cluster differences. So, where we are using actually market segmentation. Market segmentation, I mean, most of the people are using it for the market segmentation, where they are finding which segment of which people are which segment of a people we have to target. For example, you may have seen that if my let's suppose market my again shop is in a locality where there is actually different people of different natures and different salaries living. So I can actually target them. Okay, this product I have to buy, or I have to sell for this range of people, because then I will target them accordingly. So, okay, rich people in my society are only 10%. So I have to actually bring only 2% of these instruments for them, because otherwise people will not take me, and it will keep always in my stock. So this is where they use it a market segmentation to target a particular segment in a people. So exceptional students, for example, you may have seen that most of us have a normal traits. So we are not actually that intelligent. If we see on an intelligence scale, I mean most of the people in the world. So but sometimes we are saying, okay, we think that he is a very good, he is intelligent. So what are actually our benchmarks? So we are actually clustering them on the basis, for example, on the basis of his actions, how he is actually interacting with the people, or how he is actually responding to the some stimulus. On the different basis, we are saying, okay, this student is actually is going to behave in a good way. So this is type, I mean, exceptional students. We are making groups, and again medical groups, for example, on the basis of diagnostic reports. We have a diagnostic reports of different patients, and we want to treat them in a queue or together. So at that time we do clustering of different. And one more useful statement I will say you. For example, we are working in an industry, and I have a computer, to be specific, I can say that I have a processing data for each of the employee. So from that processing data, I can actually classify them, whether they are a programmers, whether they are a data engineers, whether they are a data architect. So, I mean, the question is how. So for example, if I see the most of people are the people uh, who are using Jupyter Notebook instance, who are using PyCharm, who are using Spider, who are using Anaconda, who are, so I can say, okay, these features, these 4 features they are using, so definitely then they are Python developers, because they are using only the Python tools. Again, if I see now people are using Rally, or they are using Scrum tools, so I can say actually they are actually more in the management side. So this is where we are using clustering. Then algorithms, what algorithms we are using? K-means clustering, most people are using this. There are the density models, there are the distribution models, and there are the linkage clusters. Distribution models, I mean, you can say from where you are actually finding from which distribution this observation is coming. So you are pushing the observations in different, let's suppose that some are having the chi-square distribution, while the others have a normal distribution. Then the rows or the observations which are showing a normal distribution is actually, they are actually the one, the normal distribution are actually the one cluster for me. Those which are showing chi-square distribution are actually the another. So these are the distribution, and then there is a density db scan. I don't know how many you have used that db scan. So db scan is a density basis. So k-means clustering. So db scan is very good. It is a density based, and linkage clustering. Sometimes we hierarchical. So hierarchical, when we do hierarchical clustering, so that is a linkage clustering. So, for example, if we say the one project, it happened probably 2 years back in USA. So they want to actually classify the people into different clusters, and so that they can actually formulate different policies on them. So for them, these were the 5 features they took. How much people are extroversion, how much they agreeableness, how much they are conscious towards the things, how openness, how they can actually share there, and how neuroticism they were showing. So these 5 features they took, and they rate them on a scale from low to high, and then converted them into mathematical vectors and used clustering, and then they were able to formulate actually the different policies for a different groups. So now the classification, again, as I already told that these are the 2 main, clustering and classification are the 2 main topics of a data science, which most of the people are doing work in it. So the process, it's again the process of segmenting like we do in a clustering, but here we are actually forcing our data set to actually measure, so where we are actually having these where we are actually forcing them towards that my label. So here one thing is to actually keep in mind, it's type of a clustering again, but here we have, because we have here labels already, so it goes in unsupervised, it goes in supervised learning. So the clusters are from, clustering is from supervised learning, and this classification is a special type of clustering which goes in this supervised learning. So the previous one, clustering, was unsupervised, and this one is supervised, because here we are actually forcing our observations to go into the different clusters. So how, I mean, for example, you will see that when mail is coming in a Gmail, some mails directly go in a spam folder. So how they are actually doing this? So because they have, over the time, they have collected the data, and they have seen that these type of words are using in spam. Spam is using these type of words, or advertise is using these type of words. So if my mail is now containing these type of words, so most probably whenever it comes, it will go directly to the spam folder. That's why you have seen sometimes if you get a notification from, sometimes even the notification, pay notification from your university will go into a spam, because what my Gmail thinks, they think that because it is using the promotion ads there, so that probably it's a spam. That's why it's sending it in a spam, though it's not in a spam. Again, fraudulent transactions. So we know that what are the I mean, most of the times these are recorded, what are the events are happening during when some fraudulent transaction happens. So when the same type of behavior next time comes, we actually take it and mark it into a fraudulent transaction, because we have already labeled such type of observation in a fraudulent transaction. So what are actually the algorithms we are using? K nearest neighbor. So K nearest neighbor is not like K means, it's different than K nearest neighbor. It's actually finding their density on the basis of neighbors and grouping them together on the basis of labels. Binary classifier. I mean, lot of things you can use here in binary. Most people are using nowadays ACB, hyper boosting trees, and ADA booster. We can use those classifiers also. We can use neural networks. So I mean, not to say hundreds of neural networks like CNN or CNN, I mean, recurrent neural networks. Thousands of neural networks are in place right now. Distance algorithms. Sometimes you don't even have to go actually that much. You can actually find the mean distance and then find the label for that for those, and then see if new observation is coming and it is very close to the mean of that label data set. You will say, okay, it will go in this type of data. And Bayes theorem. I mean, most of the people are have been well aware with the Bayes theorem. So Bayesian classifier which we are using is based on a Bayes theorem, where we are actually working with a probability. I mean, it's not actually making a data row to, or a observation to sit in particular label, but it gives you a probability. For example, the probability of this coming from a label 1 is 0.8. The probability of it coming from another is 0.2. So that means because it's showing higher probability with the first one, we will set it this incoming row in the first one, in the first class. Now some type of I mean, we are doing in classification, we are doing cross validation. So what do I mean by cross validation? So when I do training, during training we divide our data set into training and a testing. So when we train, let's suppose on 70%, we test with the 30%, it goes back, then it randomly selects next to train, random shuffles the data, select again 70%, train test until our model will get to the extent where I say, okay, this is the model accuracy which I want. So sensitivity, specificity, cross validation, and confidence level, these four terms are very much important for us in classification. Sensitivity means true positives. So how many were actually the positives and they come true in my data set? And specificity means true negatives. How many were actually the negatives and even my data set also showing negative? So sometimes one is important, sometimes another is important. For example, if we have to diagnose the patients which are having the cancer, we don't actually, we can actually for example, we can bear if true positives will come more, but we can't bear if true negatives come, because it will say it doesn't have a cancer, but that would have a cancer. Even if it for a one person, if it shows a wrong for a 2 or 3%, we are done. I mean, our algorithm is pretty bad because here life is on state. So it behaves on, it completely depends on your problem statement, where sensitivity is more important, sometimes specificity is more important. Then we keep doing cross validation. And after cross validation, I mean, the one good thing is to blind test validation. Blind test validation is the validation of our algorithm with the data which our algorithm has never seen. It's different than testing validation. Blind validation is the data which have never even been used for a training. So after that is a confidence level, with how much confidence you are saying that it has 82% accuracy or 83% accuracy. So it comes in a confidence. So I mean, you can go and learn more about this. Then anomaly detection. Anomaly detection, as I said, in outliers is something which behaves different than what other observations are behaving. For example, fraud detection. When we do a fraud detection or we do a process failing, for example, let's suppose that my microprocessor, I am taking the working behavior of my microprocessor with time. So every time it would have almost the same type of processes with respect to the time indexes. But if I see any time, hey, it's the graph of its processing with respect to time has shown a certain random behavior which I never expected before it. So then definitely my processor is going to fail because it is showing unusual than rest of the time it was showing. Some potential people you can actually figure out with this anomaly detection, you can figure out the people who are having some extra I mean, who are intelligent than most of the people, or who are having some other traits which most of the people doesn't contain. So because they are different than other people. So from now on we can say that we can't say that they are actually bad. We can say that they are different. This anomaly detection can show also those people, and outlier detection most of people know. So what are actually the different algorithms? Again, a regression and posterior probability in Bayesian theorem, neural networks and hierarchical clustering. Because if we have already hierarchical clustering for anything, and next time it's not behaving in that hierarchical clustering way, so definitely it is an outlier. That's why it's not fitting in my hierarchical clustering. So downside is, I mean, it's a pretty tough thing to do because these are rare events, so you will hardly get I mean, it's a very hard initially to get the training data for these type of detections, I mean anomaly detection. So you always have unbiased you always have a biased data set. So because most of the data will be normal, only few events will be these anomaly. So it's very tough to train. So most of the times you need actually to generate, or I can say you have to use a generative universal neural networks, which I was saying last time, or you have to use some other neural networks to generate the this fraudulent data or generate those rare events. Then only you can train. So it's as I already said, it's behaved by unusual activity because it's not fitting on my any of the algorithm. So then I mean, brief about the dimension reduction and feature selection. So dimension reduction is actually dimension reduction and feature selection is two different things. I mean, keep remember one. For example, I mean, I will quickly go above it because then we are left with very less time, and I have also to show you some this. So okay, dimension reduction. So dimension reduction is actually where you have heard that term which most of the data scientists are using. They are called as a dimensional curse. So if we have a more dimensions, we will have a probability of having more error, because that is called as a curse of dimensionality. So always we want to reduce dimensions to the extent where our model can actually have a less error, and we actually, and those dimensions make sense to us actually. So we don't actually want to work with the thousands and thousands of dimensions, which actually doesn't create any sense for us. And Why? What is the motivation? First, error decreases, and that's for sure because we decrease the, because irrespective of the how better our algorithm is, every dimension has some error to, because we are creating a digital twin. So whenever we are doing any algorithm on any data, we are creating the digital twin of actually physical existing condition, physical existing conditions. We are creating digital twin with the help of a data. So everything of these comes with some type of error. So when it comes with some type of error, so we have to actually reduce. So first thing is error will decrease. Second thing is reduce collinearity, or we call it as a correlation. So when we have a higher correlation between the things, higher collinearity, and they are correlated very high, and the correlation is high. So in that way, they already add a bias towards that future. That future is already getting predominant or prevalent than others. So in order to decrease that bias towards that future, that particular future, we have to actually remove or all except one correlated future. So improve speed, because now the number of dimensions decreases, definitely it will improve the speed and improve generalization, because we don't have to next time collect every other tag from our data set. Some algorithms using is PCA. So, and another is a factor analysis. So PCA and factor analysis, you will see people have using them interchangeably, but they are not the same actually. So we can, if we say the one algorithm is 1, another is -1 actually. So if one is behaving from a left to right, another is behaving from right to left. Actually, to be in a simpler terms, one is finding actually reducing from multi-collinearity to this single component, and another is finding the reason for a multi-collinearity, and it from that it's taking what is the reason, and it's only taking those features which are actually causing these multi-collinearity. So they are actually opposite of each other, but people are nowadays using them interchangeably. Now, future selection. Future selection is actually to decrease the number of variables. And keep one thing in principle, I mean, in those principal component analysis and factor analysis, the variables or the futures we get ultimately are not actually the real futures. They are the generated futures, which we generated from the actual futures. On the other hand, the future selection we are doing on actual futures. For example, again, the motivation is same. I mean, we are getting error decay, reduce collinearity, improve speed, improve generalization. But the thing is that at the end of future selection, we will get the actual futures, not the generated one. So they are actually what we have actually from our data set. So a few algorithms correlation. We are using correlation. We are using stepwise regression. So stepwise regression is, for example, we have a thousand of variables, so we take one variable out and make it as a target variable and see how much it's correlated, how much it is being properly predicted with other variables. Okay, if it is properly predicted with other variables, that means this variable is there in its information is already contained inside all those variables. So those are variables are already representative of this with some weights, but they are representative of it. So we, even if we remove this, it doesn't make any ultimately any change on our final algorithm. So regression, lasso regression, and variable importance. So most of the people have used. I don't know how many of you have random forest for classification, but random forest can also be used for to check a variable importance. So at different levels, we can take if we put a random forest for variable importance. So if we take a depth of a 3, depth 4, depth 5, depth of a random forest tree, it will give me the importance of variable at that level also. So we are using random forest for that also. So this was, I mean, introduction about the analysis. Now we can actually go in. I mean, I will actually show you some of analysis in real actually. So let me. So this is, I mean, because I can't share my local laptop, so that's of a company and that has some privacy policies. So this is the laptop I'm using, my friend's laptop, and here I'm using this Amazon SageMaker. So Amazon SageMaker, as I yesterday told that it is. Can you see my screen?
Just once
Yes,
again,
sir.
unshare.
Yes, sir. It is visible.
Okay, you are seeing Amazon SageMaker?
No, 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 no. You just unshare your first, then
Okay,
share your
okay.
screen.
I was sharing my desktop. It should actually share anything what I want, but okay. Now you can see SageMaker console.
Yes, yes, yes. चलिए इसको कौन से time is there?
Okay, so this is Amazon SageMaker, and if you go on its dashboard, I mean, yesterday I was talking about their machine learning as a service. So if I go quickly on its dashboard, you will see I'm right now inside the SageMaker. Okay, let me actually take you to the services. What are Amazon services provide here? You see, this is its servicing dashboard where you see EC2 instance, you see Lambda, you see batch, and yesterday I was saying that we can use Lambda to trigger our services. There is a EMR2 and cloud search. Cloud search is where you can actually go and check the life cycle of your different instances which are running. Elasticsearch services, you can use Kinesis and AWS, all those. S3 is a graphical database where you can actually push your data and store in the form of graphs. It is actually storing as a key value pair, where everything folder is a value and every folder name is a key. So I mean, this is a brief about the services. So then you can see this is Amazon SageMaker, which I am using mostly. I mean, because yesterday I was saying you that if you are in a data science, so irrespective of how powerful your local machine is, that will never be enough for your compute resources. That's why we mostly go for those Azure or for Amazon or for Google Colab. Colab is also or for this Watson, IBM Watson, and I'm using right now SageMaker. So first thing, I mean, I'll give you a brief introduction. This ground truth. You know that when we manually do labeling jobs, we have a labeler data set, and then we go manually and do one by one labeling job. So that's pretty tough. Right now, this Amazon have providing one service that's called the labeling jobs. You can upload your data set here and define the rules for your labeling, and you don't have to go then and label manually. It will do for you. And ultimately, your trained data, I mean labeler data, can be either pushed to S3 or any other Redshift or any other database, depends on what your requirement is. So there is a processing jobs. It will show what are the jobs which are right now in a processing state, and there are the training jobs which I was saying yesterday. So what happened in my local machine, whenever I put training instance, it will actually hang my that notebook instance. I can't do anything unless my training will complete. But you have here one such useful method. Actually, you can push your training job into a container, and then that will keep running back in a container, and you can anytime go and check its life cycle going into these training jobs. You can use some algorithms. I mean, some algorithms mostly these you can find algorithm. They have one bunch of algorithms, for example H2O, facial recognition, text similarity. These type of algorithms you can directly take them and can use in your notebook instance. And one thing is actually good here, you can also create your these algorithms and can push into their container, and they, if they find it very useful, they can give you I mean they can give you some money for that. I mean you are giving them algorithm and they can add it in their marketplace. So they have a marketplace there. So you can do hyperparameter tuning here in your trained models, and all those things. I mean, you can check your models here. You can have endpoints. I mean, when you deploy your model, that will generate some endpoints. Then you can do endpoint configuration. Then you will use Lambda only to actually, and you can do all those things here, I mean, if we go inside this, it will take a lot of time to do all those things. But I can say top few services which I like is Lambda, Glue, AWS SageMaker, and S3, and Redshift and EC2 instance. So these 6 services together is enough for us to from complete deployment to working to installation. Everything comes in these 6 services. So now let me take you.
Hello.
Okay. Yes.
Sir, you just said that there are many algorithms which are available. So, is it the thing that always we can in some step, let's say if we specifically talk about the NLP, we may have the BOT algorithm and the GPT like the algorithm. Is it the scenario or they are only?
Your voice is pretty much breaking. I mean, I heard only some NLP.
Sir, I was talking about the algorithm. You just said that many algorithms are there, right? So, can we say that all the state-of-art algorithm are there? Maybe the GPT as well as the BOT algorithm, which are specific for the NLP application and very good in the use right now.
Okay. I'll I mean actually send you marketplace also. I mean I will get some screenshots and send you. But you can even go there. For the 1 month, for the 1 month you don't have to pay. Actually, you can create your account there on AWS. For the first month you don't have to pay, and I mean I shouldn't say it. Actually, I opened 3 times it and doesn't pay from 3 different IDs for my personal learning. Though it's not a good thing to appreciate, but yes, from my personal learning, I 3 times created 3 different accounts, and because I don't have to pay for a first month. And then you can actually go into their marketplace. They have lot of these algorithms from different fields. Yes, they have different fields. They have from NLP, they have from facial recognition. If you remember yesterday, I was sharing one PPT, and there I was actually comparing the different algorithms given by a different these machine learning as a service providers. So yes, they have NLP, and I will share you their screenshots also from marketplace.
Okay, sir. Thank you. Thank you.
Yeah, you just should email me. I will finally, I mean, at the end of this section, I will share
Yeah,
email ID.
sure.
So I mean, the one thing, I mean, which most of the people are using is like this notebook instance. So I have already created one notebook instance. So if for you people, if I create, I mean, one more notebook instance, for example, here I will show you actually what are the things they provide. One is a notebook instance name. Second is a type of a notebook instance. So you can see here lot of types of notebook instance I can create, and these are actually the different computer sources. So MLT2, for example, it would have a 4 CPUs. If I go inside these C instances, it would have a GPUs. So you can, according to your use case, you can actually create, and there is a accelerated computing. So P2, P3, all those. So according to your use case, you can go and create any type of an instance. So you don't have to buy actually everything. You just have to pay on a use. The time for which you use it, only for that time you have to pay. For the training time, just you have to pay. And then is another thing is elastic inference. So elastic inference you can take, for example, let's suppose, okay, I want only for some training. Out of 100 training, let's suppose I want only few trainings to get trained on more computer resources. So at that time, these Amazon people have given us that I mean freedom that we can actually use any of these as resources added upon the already resources. So already resources are of my notebook instance type, and I can add more resources with this elastic inference. So then it's a role created by you. So this role is actually it's a, I mean, for me, I have given a root access. So for example, I can do anything now inside my notebook instance. I have a complete access to my databases, all that stuff, because I am as a root. And sometimes if you are the administrator and you don't want, for example, your students to, I mean, do things with other resources, so you can actually create a role with a different different accesses. So then there is an this called as a network. I mean, if you are working in a VPC, in a personal VPC, for example, when I'm working with a GE, we have a personal VPC. I mean, my organization, they have created their own VPC where we can work within that VPC, so that our data has a higher security. So no one. And here you can actually align your Git repository to it. For example, you want to directly take or push this data to Git or take back from Git, you can directly go and do this thing here. And then these are the tags you will ultimately say, I mean, you tag value pair, you can add them here and you can see them in edit configurations where you are actually finally seeing the life cycle of your notebook instance. So this is how we are creating actually. I have already created one notebook instance yesterday night. I mean, in order to show you today. That's why. So this is the notebook instance. It's opening, for example. Okay. So, for example, I have actually collected few examples for you. I mean, in order to actually show these. For example, let's suppose, I know that most of people may have learned about the loops, but I will, give brief introduction about these. So, for example, loops. What are loops? And this is how I ran it notebook instance. Now I'm like in my Jupyter, local Jupyter, everything. So this is warming up with the loops. For example, let's suppose so this is a math library, then collections, you know most of them, and NumPy is the numerical library, and you can say for most of the mathematical operations where you can store your these data. And then there's a Panda library where we store data as in the form of a data frames and do many things which we can also do in a NumPy. So, and they are mostly because mathematical operations and all those steps we have to do, we will not go with the trivial data types which are present in like integer, arrays, lists. We will not go with those, because here mostly we have to deal with the high-end mathematical operations. That's where NumPy and these Panda comes handy. And then there is a matplotlib. So it is like you have, I don't know how many you have used MATLAB. So like it's extracted from that and created initially from that. So it mostly helps us to draw different type of graphs, different type of visualization things. So percentage matplot inline means, hey, I am saying it or I am forcing it. So whenever you have to plot a graph, plot it on the same notebook instance where I am using. So loops, I mean, it has loops different than loops using in other language like in Java, where we have to create for I is less than 100, I plus plus, I running from 1 to 6. So there we have a different, but here you can directly do for I in a range 0 to 10. So it will take it, for example, and print for you. Let's suppose, okay, let's first restart, I mean, for you people to clear the outputs actually. Otherwise, because I created those notebook instance yesterday, yesterday night. So simple about loops actually, I mean, it will print, and I in a range, I mean 0 to 10, if we give, it will start from 0 to 5, because I'm saying in a range of 5 only. So this is actually the step. What I want is to a step for I in a range 0 to 10 and give a step up to, for example, you see 0, 1 is missing 2, 3 is missing 4. So it's taking step up to 2, 2 to 4, 4 to 6, 6 to 8. So we can also take like a plus. So like this 0, 1, 2, 3, 4, and we can take also, and it's adding simple operation, and we can take a 25 step. So amount 25. So let's suppose that we are creating one combinator here, and it's a nested for loop for this in this, for this in this, for this. It may create a different combinations. For example, I pass a 200 to it, and you can see here actually these many combinations are possible for a 200. So if I actually, this is just to show, I mean, how for loops are working here. And I create a total from a range of 100 to 600 and jump off 100. So let's suppose here, and it gives me length. And if I plot now, you will see it has a this type of a exponential increase it is showing in so as the number increases, and the number of combinations also increases in an exponential way. So this is I mean, simple about the loop, what we are using for loop. So we are also using while conditions here. So this is the one notebook instance, I mean, for the loops. Then there is one more notebook instance for sequences, where how we are using these sequences, like lists, tuples, and slicing. So for example, let me first restart and clear. I don't know, I mean, how much it actually makes sense. So again, I'm using same libraries, for example. So you see here, lists can directly, we can actually initialize list like this, directly giving names, and a length parameter is something which gives me length of a list, and indexing is done in the way 0, 2, 3, like the way we do in a Java also. So script, and indexing, and you see, because third is doesn't exist here, 0, 1, 2 exists because it starts from 2 and set, it starts from 0 and ends at 2. So it will throw list out of index error. So we can also do indexing from this side, which is a very good and handy sometimes. So it's at a -1, -2. So we can do like that. For example, you will see here. So -1, -2, and here you can see we can directly do the concatenation here in this strings. So with the plus. So you don't have to convert them like string plus this. You can directly do string concatenation with this plus. So you can see high duck, David duck, Louis duck. So you can also see in lists here. Its data types. It's not always I mean, necessary to have a same data type inside list. You can create a mix. For example, list of, this is a list, this is a character type, this is integer type. So you can create list of this type also. So in order to add a new entity, you can do append. So append will actually add it as an entity. You see that, but extend will again add a new list. When we want to add list to the list, we can do extend. If we do at the time append, you will see, for example, if it is a list and I will do append for you people. So at that time, what will happen? It will add it as a list, because already I told that you see it added it as a list, because I told that we can have a multiple data types inside the list. So extent will take care and it will add it as an entity rather than list. So you can actually do like this addition, simple, and it works like extend, you can see. And then you can also insert with the indexing, and you can delete with the indexing, for example, and delete. Oh, my network. Okay, so you can see now I deleted at the 0. So initially I included this, and now I deleted with the indexing of a 0, some entity. So you can do remove, because you can delete with index and you can remove with actual value. You have to, if you use remove, then you have to pass the actual value. So for example, I passed the Donald Duck, and so Donald Duck was in this here. So that's done now, removed. So you can do sort functions on it, sorry, like this, sorted. And if you can do reverse sort. And one thing, for example, here is, you, if you want to see what are all the functions inside, you can do dot and tab. So it will show what are the functions inside the list, like sort, reverse, remove, pop, insert, index, and all that stuff. So okay, so now this is something slicing. So in lists you can do slicing. For example, I want it to take from 0 to 2. So it will take the first, and but it will not take the last. For example, it will take 0, 1, and because I'm saying from 0 to 2, so last will not be included. The last index will not be included, and everything till the last index will be included. So it will take 1, 2. For example, if I wanted to print 1 to 4, so it will take 1, 2, 0, 1, 2, 3, not the 4. The last index will not be taken. So you see 0, 1, 2, 3, and not the 4, not 25. So for example, I can do also everything, give me everything above 4, above the index of a 4. So it will give everything above the index of the 4. Give me everything below the index of 3. For example, that means after, what is coming after the index of 3. So 0, 1, 2, and 3. What is, because it will include this. I told already that initial is included. So what is in 3? 16. So it will include a 3 also. 0, 1, 2, 3. So it will include this and after everything. So that's it. So when I give, and this means above and below everything. So this doesn't make that much difference. So it is saying below and above everything. So I can do also like this to jump, then make the jump. So it is making jump of a 2 on index. For example, 0 is present, 1 is not present, then 2 is 0 is present, 1 is not present, then 2 is present, 3 is not present, then 4 is present, 5 is not present, then 6 is present. And already, as I can say that we can do the indexing from this side also, which starts with a minus. So the first one is a -1, for example. You see it is a -1, so it means this. So give me everything, as I already told that the last index is not taken, so its index is -1, so it will not be given. So it will give this -2 to the -3, this and this. So similarly, we can actually give assign the values like on the slices. For example, here you can see actually I have modified the value of a 9 and 16, so directly assign it 4 and 9. Oh, sorry. So you can actually delete these, and I mean you can have a length. For example, for this is length is 0 because this doesn't have anything. Then there's a tuple. So tuple, or you can say these are like immutable, and where you can't change. Once you create, they are not mutable, they are immutable, where you can't change. Once you created it, you can't change it. For example, you see 1, 2, 3, 4, this is a tuple, and now we can do, for example, indexing on, we can print them with the indexes. But for example, here you see I want actually to change it. I want the integer 0 to include something. So it will say tuple object don't support item assignment. So we can't do assignment here. We can't change it. But tuple. This is called tuple unpacking. So it's very much useful when you are, for example, you want from your Python function to return 6, 7 things together. Like in Java, if you want to return 5, 4, or 6 things together, you actually have to create first object class, and then you have to actually assign value to each object. Then only you can actually which there are called as a data object classes or data objects to return from your function. But here you have that freedom that you can actually return in form of a tuple and then do tuple unpacking. For example, A and B, and if I print, I mean, for example, AIB, so it will have done a tuple unpacking. Do A comma B. I don't have my laptop with me, so this you can see it done unpacking. A is assigned 1, B is assigned 2. So similar fashion like this. So you can use an enumerator. So enumerator is just I mean, enumerator if we want indexing also. So in enumerator will give me index of list also. So we can use this argument like my args. Now you see the print ABC. So I'm actually giving together 3, and I can use this star my args. So when we have a multiple arguments to pass together, we can give as a star here. So it can pass actually the multiple arguments and it can print them. So I because it is a tuple unpacked. So this, and it will do their tuple unpacking and print all them together. So this is called as a tuple unpacking. So let me stop them, otherwise this and this shut down. Okay, so now third one is a dictionary objects. So dictionary objects are pretty much useful in our leave this and this. Okay, dictionary objects, they are pretty much useful for us. I mean, we use dictionary objects a lot. First let me clear it. Unless you will not stop your notebook instance here in AWS SageMaker, they will keep your notebook instances running. And when you this is a good practice. I mean, it came in my. This is a good practice whenever you, if you actually register for this SageMaker, then make sure that each time when you log off, completely shut down your notebook instance, because as I told that they are actually costing pay as use. So as you use, they will make you pay for that. So if you keep it running, that means you are using it. So every time you go log out, you actually shut down this notebook instance so that they can stop billing. Okay. So now this is a notebook instance. This is what dictionary is. So we can actually have this key value here. This is a key, this is a value, and this is how we are initializing dictionaries in Python. So this is like, and in the way of lists where we are using index key, here you can use a key and to get the value of that. For example, capitals Italy, and when I will get a room back because its key was Italy and its value is Rome. So if you see, this key is not present there, so it will throw me array. For example, if I say that this is assignment, I added one more key here. I added one more entry in my dictionary to span. I said that Madrid. So now let's suppose that does our list contain Germany? No. So it doesn't. Sorry, does our dictionary contain Germany? No. So it doesn't have this key, so it will throw error. It will say no, this key is not present. There is a key error. So, and this we can also use in our conditions. And for example, Germany in capitals will be false, Italy in capitals will be true. So these things help us in when we do programming in conditional looping. All those things will help us because we generalize things there. So for example, I created one more dictionary, and we can actually, for example, you see in lists we can directly add them, and they actually work like dot extend, list 1 extend list 2, but here we can't do that. It's unsupported format that we can't. We have to do other function that's called update. So update is there, and here like the way we were used in lists, we used to delete any intent any entry with the help of indexing. Here we can delete any entry with the help of key. So delete. Now you see that we don't have any more there United Kingdom. And for example, you can also give this tuple. I mean I gave a tuple as a key. I can do that and then use tuple as a key back and to get the value. So I can, okay, this thing is very important. So hash. So mostly when we have working with the data security things, we rather than giving directly value, we keep them as in a hash. So hash of a key and hash of a value. So then over the in network, we only use hash values. We work with the hash values and ultimately get back from a hash. We can get actual hashes are not compatible to the, so they are not security. They will not be the security threat. So for example, now this is a length, a similar way how we used to get a length in a list. And then for country, this is a for loop running, because I said for country in a capitals, it will give you the keys. For example, you see here it will give you the key list when I use the United States, France, Italy. So you see the United States, France, Italy. So it gives me keys, or you can do capital dot keys. It will give you a key as the form of a list, and then you can print each of, for example, you see the list. It's a list in the form of list keys, and you can do actually then list of the keys like, and then you can get a value. For example, capital dot value, it will give you values, only the values, or you can do dot items, then you will get key plus value pair in each. And this is how we are actually working with the dictionaries. And then there comes one more data type which is pretty much important, that's called sets. So containers, for example, you will see this is a set here, and this set, I mean, which looks pretty simple here, but when we work with the set operations, rather than actually doing all those things manually, we use sets and do all those, and those all operations like intersection, like disjoint, like all those, I mean union, all those are actually available in sets. Those operations are available in my UC. Add, clear, difference, update, intersection, disjoint, is, upper set, pop, remove, union. So all those operations which we use on sets, they are already here. Symmetric difference and all those things. So they are pretty much useful. These are its different methods which we can use on it. So for example, Africa in countries, it will return like it was returning earlier too, and you can do add like this, you can remove like this, and you can print them like, I mean, you can loop over iteratable. So it is a iteratable object. So this is a dictionary. You may have actually learned about these things, so but they are pretty much important. So, and also given to me that I have to tell about these things, so I can leave it and I can stop it here, like shut down. So now the another thing is the comprehensions. So comprehensions is again pretty much useful thing. So because you can say, I mean, you can actually argue we can write everything what we write in a comprehension, we can write also in a for loops. Yeah, we can do that, but it's a good practicing, because as now Python is giving comprehensions, we can use a comprehension, and it also reduces the your code time. I mean, you can actually code quickly with the comprehensions. You don't have to actually write long loops. You can run in a single line of code. They are inliner, like in Java. I don't know Java. How many of you people are working in Java? So Java comes with the annotation like that implies. What we write in a common document, that implies. So those type of implementations we have in Java these days, and those are called as inline codes. So those inline codes are like comprehensions in Python. So for example, you see this is a simple for loop, and I can what I have done with the for loop, for I in range of this and give me the squares of this. I can directly do this thing in this one comprehension. It will again return me the same list, but in a one line of code only. And even if you see, for I can apply conditions here. For example, this thing I can do in a for loop, but this thing I can do here also with a comprehension in a single line of a code. For example, what I am doing here, for I, get the I, do its raised to power to, I mean, squaring, and also if its square divided by 4 returns me a reminder of a 0, so then only give me the list, otherwise not. So that's why you will see only those which are divisible for 4, 16, 36, 64, 100. That is only those entities will come. So this is where actually it's helping me. So for example, here we can create also dictionaries. It may return like a dictionary, comprehension dictionary, rather than, I mean, otherwise we have to go in a for loop and create this. We can directly make it like this. And for example, countries and countries by capital, I create the same dictionary what I was showing in last time. So you can see here, and like same thing what I did actually, I put a condition, for example, 2 loops together, and those 2 loops I can do in a comprehension again. For I in a range this, for j in a range this, then return me a j. So for example, you see the huge list I got returned here, 1 1, then 1 2 3. I can do this in a one single line of a code rather than writing the huge loop. So you can see again it's returning the same. So this is how we are using comprehensions. So stop it and close it, leave, and comprehensions. Okay, any instance which will be running, it will be shown as here green. So you can go and start. So there are actually so many, I mean, I have created so many things, but I don't know whether I'll be able to show all them. So for example, let me show actually now one use case actually, not going into the numpys, and otherwise I had some Jupyter notebook instance created for NumPy introduction, where I can actually show how we are creating, how we are indexing, how we are doing mathematical operations. But because of a time, I have only 7 minutes. Let me show actually this thing. This is pretty much one use case. I mean, just to load a weather. Yesterday I was showing you these this site where I can get the data of. So here today I loaded a weather data from that website actually. Sorry, restart and clear output. Okay, same. So just here I'm showing how we can load actually the data. For example, URL lib, I mean, when we have to load directly data from some website and all that stuff, we can directly use URL lib and give the address, and it will retrieve data from that REST API. So this is a REST API. So API concept most of people would already have. So I'm saying it load this and give a name it to readme.txt. So if we go then inside this, and I would have a readme.txt here in this, and that will be loaded in this readme.txt. So this one. So you can actually open it here. So you can read it here. For example, it will say different things about what data set it is and what are the variables and type and all that stuff is written inside. And I have used actually this only station text. So where actually it has information about a one station like ID, at which latitude and longitude it is, and what is the elevation of it, in which state it is situated, name, and what are its operations like HCN or CRN, and all those things. I mean, which I actually am not interested that much, because I'm just doing overview of it. So for example, as I already told that I also now got that station dot, which I said that I was interested here. So in my readme, so these station.txt. So I am saying it load this and give it a name station. So here it's a simple format. I mean the information which is given. So it's saying that it's a .txt. So if you know already working with a .txt, so they are comma separated, for example here, and it's saying the first 11 characters are actually the ID. Then from 13 to 20 character is a latitude, and then there is a longitude, and then there is a elevation. So I'm same thing I'm saying here. I'm saying okay, but remember that this example I'm giving you this use case using only NumPy. So I can do these things with pandas on also, but I had actually for you formulated them separately as pandas use case, but because of timing I don't think I can be present everything, but I can actually give you those notebook instances and these data sets if somebody is interested to work and see. So now you see that I have put them comma separated like 11 characters, what is written here, then there will be the 9 characters, and because I have to take care of the spacing between these two, that's why I am giving like this, and delimiter. Then I am giving name, ID, latitude, longitude, elevation, state, GSN, HSN, and WMO. And then I'm giving 11 characters of, because it's a character string, so 11 unique character, and then decimal type format, then which here we called as a floating format, floating format, floating format, floating format, then Unicare of a 3, Unicare of 31 characters, and like that. And then auto strip means anything outside this, just drop that. I don't need that actually. Okay, this is how it's doing actually. It loads it. Now length of station, I got these many entries from. So if I actually show you. So these are the top 10 actually is for or top few, actually top 6 actually it's showing. So these are the entries actually shown by my stations. Okay, so now if I plot longitude and latitude and mark size 1, okay, ms, and you can write ms also for this mark size. So this is where actually these locations are present, their longitude and latitude locations on the map. So stations, longitude and latitude, you see how they forming the map. So it's pretty much they are covering the whole USA, because I took it from the USA side. So it's pretty much they are covering the whole USA. So this pplot is the matplot library I'm using. And now if I say, for example, okay, I want only California stations. So for example, this, and plot its longitude and latitude, you will see this is a California area. These where the stations in California are present and almost covering everything in the California. So now there is a Pasadena. So let us suppose that I want Pasadena, and I want all those stations which are starting with the proper Pasadena word and indexing with a 0. I mean, that means again starting with the Pasadena. So these are the Pasadena, and this one is, so most of these are WW, I mean this WESC, so I don't care about what they are, but this one is a little different, SCN. So for example, we do our analysis on this. So retrieval for this from this ID, because if you have seen that in readme text, they are telling that every information for every station is stored in its ID .dly file. So here you can see, so what is DLV? So they are saying that it is store id.dlv. So what I did here, actually same thing I got here, address, and then I took this ID 679 USC 679. This is here ID .dly, and I am saying it keep a name .pasadena dy, for example, and load it from me. So when I loaded it, so now there is a one library actually. I mean, this is a get weather library. So this is a universal format for it, and I have this also stored here. You can actually get a look on that. So, but I mean now, for example, I'll for you how it is. So this is the function, and if you give a station name, then you give elements, and then you give a year, it will return you. For example, here station name is Pasadena. I want minimum and maximum temperature, and for the year of a 2000. So this is directly, I can use this function directly, and it will return me. For example, it is giving me minimum and maximum of a Pasadena for the year of 2000, because for each month and for each day we had a one tag for each day. So therefore we would have some 365 tags of it, and some of them are nan, so it will come as a nan for me. I mean, those values are not there. So let me actually shut down this and show you. This was more to the loading, how we are doing loading. Stop it, close it, leave. Okay, and it was this. Shut down. I think we are over time, but okay, let me at least run quickly through this. So how we are actually dealing with the missing values. This was a very good, I mean, then I was teaching, actually learning how we do smoothing of time series and all that stuff, but okay, maybe. So this is import get weather, what I import initially, and this is how I used get weather to get the data for a Pasadena. Now if you see, I want to get a mean, minimum and maximum. If we do directly like this, you will see it is showing nan. So why? Because already you remember in the last exercise I showed you that there were some nan values. So because there were the nan values, so directly using on the numpy mean, it will not return meaning, it will say nan. So for example, if you see here, so there are some nan values, so that's why it's returning finally nan. So actually, so if you see here, so anything plus to nan is nan. So there is one function. is nan, which will give me whether positive, false or a true on a boolean value for where we have a nan. So for example, here we have a nan. These are true. These locations very true. So we can actually get the total number of names. For example, this is one brute force type of programming we are using so often. For example, false, true plus true. It will return me 2 because the number of trues is 2. So for example, now I want to see actually how many names are in my max temperature. So min temperature, sorry. So it's the 15 intervals are those where we don't have any entry for a name. So there is one more function. I mean, because I told you this mean and max, it was not giving me here mean and max, it was returning me nan here. But if we use the function of a nan min and nan max, so it will exclude those entities or entries where it's a nan and give you max value and min value. So but we can also do what we can also do actually, we can actually get the time data where is nan and actually assign them the values of nan mean and nan. So because we can get here without excluding the values of nan, we can get the mean and we can get a max, we can get also the maximum, minimum and mean. So for example, we got a nan mean, we got a nan max, and we are saying, hey, np dot is nan true, all those places where Macedonia doesn't have a maximum temperature and minimum temperature, they are nan, update them with the mean temperature. So this is, for example, how I treated them, or how I actually replaced the missed values here. So for example, this use case they may be fine, but for other use cases mean doesn't work. Maybe median, mode, interquartile or interpolation may work. So for example, here you see these are all values where I have introduced the mean values inside these. So they were earlier nan. So now if we do the plots, for example, this is plot. Now we can plot. Earlier we can't plot it because it has some nan values. So I mean, I think I'm already over time. So there are so many things to do it. I mean, you can finally create some fancy graphs, for example, in it. If you see here, so this is one axis, for example, array, and this is another array, and I, for example, missing some here, and I want it to interpolate. So rather than taking a mean, I can interpolate. For example, you can see here. So these were the actual values, and these are the interpolated values. So because earlier they were missing, now I make them interpolate. So you can use the interpolation function for that. So many things you can do actually. So you can do interpolation more. So how many intervals I want? I want 30 intervals for the interpolation. So you can do that thing also. So like we had now Pasadena, this we get the data for 2001 max min, and we do the function which at the time of UC, which are only good, and I want for them to do interpolation rather than using the mean, which earlier I used. I can do now interpolation and can pull out now max and mean. So there are actually more things. So I will actually share you all those files, and these files you can actually run them in your local and see how they are working, because we are already over time. Anybody has any question?